Good evening, students. So we'll proceed today with the next topic, that is applications of Gauss Law. So this is my fourth video of chapter 1. I hope you have seen the first three videos. If you have not seen, please watch all the previous three videos. So now the topic we are going to start is 1.15, last topic of this chapter, applications of Gauss law. So we did yesterday that flux can be written in two ways. One is, by definition, it can be written as E dot S. It's a dot product, so flux is a scalar quantity. Another way is by the Gauss law, that is, flux is equals to Q by epsilon naught. So you can calculate flux by two ways. First way, if electric field is given to you, and second way, if the charge enclosed by the surface, by the Gaussian surface, is given to you. So these are the two prominent formulas on which numericals will be asked in the exams. And these are another important topic, applications of Gauss law. So this Gauss law, that electric flux is equals to charge enclosed, Gaussian flow through the surface S, is the charge enclosed through the surface S divided by epsilon. So this we are going to apply. So first application is the field, electric field due to an infinitely long, straight, uniformly charged wire. So here I have a infinitely long. Students, this is on page number 37 in your NCERT. Please open your NCERT books. So this is infinitely long, straight, uniformly charged wire, and it has uniform linear charge density lambda. So lambda is the uniform charge density. The wire has obviously an axis of symmetry. So this is the axis of symmetry, that is. So look at figure A, figure 1.29a. Suppose we take a radial vector from O to P. So this is point P and this is point O here. So, and we rotate it around the wire. So take this vector OP, this point P, and rotate it around the wire. So you'll get this this surface. Now on all the points P, P dash, all these points are equidistant, right? Radius, all these points are radius, P double dash. They are completely equivalent with respect to a charge wire, because this is a circle and all of them are radius. So all of them at the same position from the wire. So magnitude of electric field is same at all these points on the circle. Now the direction of electric field at every point is radially outwards If this is a positive charge wire, means the linear charge density is greater than 0, means it is positive linear charge density, positive wire. So from positive charge, the field lines are outwards. So this is the direction of electric field here and here and here in this direction. So this is the direction of electric field, radially outward. Now let us take two pair of line elements P1 and P2 of the wire. So this is P1 here and this is P2. The electric field produced by P1 and P2 when we so due to P1 this element, so the field will be radially outward in this direction, and due to P2 it will be radially outward in this direction. So this field will have two components. So this field will have two components, this one horizontal component and vertical component. This again will have two components, horizontal component and vertical component. These two components are equal and opposite and they will cancel out each other. So net electric field will be along E only. So the components which are normal to the radial vector, they cancel out each other, and this is true for each pair. So the net resultant, the net electric field will always be radially. So if we take, so this is the figure, because this question will not be asked for more than 2 marks, so you need not to discuss this thing, this is just obvious. So if I draw a Gaussian surface, so this is a surface that I have assumed by myself, not a real one. So at any point we have just studied that due to this whole wire there will be the electric, this is the electric field component, and the direction of the surface is also, this is n cap, and this is the direction of electric field at this particular point, and if this is the point, then it will be, E will be in this direction. So that's figure B. Now the flux will come out through the surface, so through this curved surface and to the top surface and the bottom surface. So what is the angle here between the surface and the electric field? So electric field is in this direction, and so the angle is 90. So flux is equals to E dot S. So here if theta is equals to, that is magnitude of E, magnitude of S, and cos theta, and if theta is 90 degree, so if theta is equals to 90 degree, then flux through the surface will be 0. So obviously field lines are, there is no field lines which is going out of this surface, so all of them are in horizontal directions. That is why flux through the top surface and also flux through the bottom surface is 0. So there is no flux, so the only flux coming out is through the curved surface. So from where you are going to start, and this electric field, you can see this is radius r, so it will depend, so this electric field depends on this radius r. Okay, so as the field is, as this wire is infinite, so this P point can be anywhere, so position doesn't matter. So electric field is radial in the plane cutting. So from where you are going to start your derivation? So let me start the derivation. This is how you need to write in your exams. Electric field is everywhere radial in the plane cutting the wire normally, cutting the wire normally. So, and the magnitude of the electric field will depends only on the radial distance r. So now to calculate the field, now we are going to calculate the field. We have to we can write from the figure. So this is the figure that you need to draw. This figure is not required in the exam. This figure you need to make. This is figure 1.29b. This you can draw. Okay, so this the length of this Gaussian surface is L and the radius is R. Now since the field is everywhere radial that we have written, flux, so cutting the wire, so field is everywhere radial, so therefore flux through the two ends of the cylindrical Gaussian surface is 0. So cylindrical, so both the ends of this, so this end which is there, this end and this end, so flux through them is 0 because the angle is 90 degree. I have already discussed. So the Gaussian surface is 0. So first point, second point. So this is not related with this, so you can write it. You need not to write first point, second point. This is just for you to keep in mind, because it will only be of 2 marks, so you don't have much of the time to write down all the details. So just draw this figure and write down these 2 lines, and after this so as the magnitude depends only on r, so this magnitude is constant because for all the curved surface that is at distance r, so the surface area of the curved part will be, so E is constant at the curved surface of cylinder, curved surface of Gaussian surface, you can say is constant at the Gaussian surface. And what is the surface area of the curved part? So surface area is equals to, we know the formula, 2 pi r h, so here h is equals to L, so that where L is the length of the cylinder. So now what will the flux through the Gaussian surface? So flux through the Gaussian surface is equals to, so flux through the Gaussian surface is equals to, obviously the flux through the curved cylindrical part of the surface, flux through the curved cylindrical C1. So through the curved cylindrical part of the surface because top and bottom surface the flux is 0. So that is why flux through the Gaussian surface is only through the curved cylindrical part. Now we'll write it through the definition. So flux through the Gaussian surface. So what is flux through the Gaussian surface? So flux is, we know flux is equals to E dot S. So by definition here we'll be using this. So E into 2 pi RL. So E into S into the angle between the surface and electric field, that angle is 0. So that is cos 0. So cos 0 is 1. So that is the flux through the Gaussian surface. So this we have written by, so flux, and that is by definition, and this we will be writing by the Gauss law. So this is definition of the flux, and then this is the Gauss law, charge enclosed by epsilon naught. So this is Gauss law. So phi 1 by the flux through the Gaussian surface, and the flux through the curved part of the surface, and that will be written as Q. So what is this is Q by epsilon naught. So charge enclosed. So now students, here we know that lambda equals to the charge divided by the length of the wire. So this is the linear charge density, lambda equals to Q by L. So Q equals to lambda by L, and so here we can write Q as lambda by L, so writing it as E into 2 pi RL is equals to lambda L by epsilon naught. So L will be cancelled out, and we are left with E equals to lambda upon 2 pi. So this R will come this side in the denominator, 2 pi R, 2 pi. So let us write the constant first. So it's better to write the epsilon naught first. So lambda upon 2 pi epsilon naught R. Now this is the magnitude, and how we will write it in vector form. So in vector form, this is the E. And what is the direction? Direction of the E is this. So students, so simple this derivation. Just you have to write flux. So this way we have found the electric field at this point. So students, these two formulas of the flux, we have just equate them. So, and we have calculated E from here, surface area 2 pi RL, Q charge enclosed, that is equals to lambda into L by epsilon. So simple derivation. So need not to get confused. The important thing is that we have already written that N is radial unit vector. So electric field is everywhere radial in the plane cutting the wire normally. So this is the same thing as this N vector. Still you can write that N vector is radial unit vector, which is radial unit vector. And now the important thing is that this direction of E, which is n cap, so it is important to write. So E is directed outward if directed outward if lambda is positive and inward if lambda is negative. So that's all. So you have told the magnitude and the direction. Now the next application of the Gauss law is field due to uniformly charged infinite plane sheet. So the second application is the field. Field means electric field. That is what we need to find out. Electric field due to a uniformly charged infinite plane sheet. So students, we clearly know we are dealing with the flux. So flux is equals to E dot S, E dot A, that is the definition, and this further equals to charge enclosed by epsilon naught by Gauss law. So simple. So we have 4 variables, 1, 2, 3 variables. In fact, epsilon naught is constant. So E we have to find out. So area and charge enclosed, these are the 2 things that we need to write. So charge enclosed, we already know in advance that if this is plane sheet, so for plane sheets we have like surface charge density, and that is given by nu by A. So Q is equals to nu A. So this is so simple. So we know the value of Q. So just A, we have to write the area and simply equate and get the answer. So let us do this. Let us find the field due to uniformly charged infinitely plane sheet. So this is the infinitely charged plane sheet. It's positive charge, uniformly distributed. Now this we need to write, let nu be the sigma be the uniform surface charge density of the infinite plane sheet, and we take x-axis normal to the given plane. So this is our x-axis. By symmetry, the electric field will not depend on y and z coordinates. Of course, the field is only along the positive x direction and along negative x direction. And electric field will be parallel to the x direction. Now we need to take the Gaussian surface. So here the Gaussian surface is, we can take as cylinder also, we can take it as a rectangular parallelepiped, that's the same thing, no difference. So we can take as cylinder also. So this is the Gaussian surface that we are taking. So this is the cylinder. And now how many surfaces do we have? So we have surface 1, we have surface 2, and we have surface 3, which is a curved surface. Now the total flux will be the flux through all the 3 surfaces, but here through this surface, the curved surface, this is direction along the y direction and field is along the x direction. So the angle between E and surface is again 90 degree, and again the flux is 0 through this surface because field lines are coming out. So there is no field line going out to the curved surface. So that is what we can see clearly. But if we write it with formula, then also flux is equals to the angle between the surface and the electric field, and that angle is 90, so cos 90 is 0. So how shall we write in the, so from figure, so we can write from figure, only two faces, only faces 1 and 2 will contribute, they will contribute to the flux. So only the phase 1 and 2 will of the Gaussian surface if you want to add, you can only add this thing, that only phase 1 and 2 of the Gaussian surface will contribute to the flux. This is the first point. And where will the electric field lines? Electric field lines are parallel to the other faces, and that is why, so electric field lines are parallel to the curved surface. So I discussed in the earlier video also that if this surface is parallel to E, then only the direction of this, taking this area as vector, so the direction of this surface area will be perpendicular to the area. So the angle will be 90. The angle will only be 90 when the surface is parallel to E. So obviously surface is parallel to E. So no field can come out. No field can cross the curved surface. So therefore, so are parallel to the curved surface, therefore do not contribute to flux. Therefore don't contribute to total flux. So it means flux will only be contributed by phase 1 and 2. Now unit vector normal to the surface here. So what is the direction of this surface? N cap minus n cap in this direction, and it will obviously be n cap in this direction. So this is, so don't take it as n cap, you can take it as j cap or any direction, because this is n cap positive x direction minus n cap negative x direction. So the net flux through both the areas, clearly it will be, so the angle here between this the area vector of the surface and electric field is 0 degree, and here also the angle is 0 degree. So total flux, like we have written earlier, total flux by definition to surface 1 and 2 will be E dot A plus E dot A is equals to the net flux through the Gaussian surface, and that is the charge enclosed, that is Q enclosed divided by epsilon naught. So this is by definition of the, and this is by Gauss law. So in last application also same thing we did. So there was flux through the curved surface, and here the flux is through both the ends. So that is the difference. So now this will comes out to be angle between E and A is 0, so cos 0 is 1, so EA plus EA will be 2EA, and that is equals to, what is charge enclosed? We have just written the surface charge density is nu, so nu equals to Q by A, and this implies Q is equals to nu A. So put Q is equals to nu A divided by epsilon naught. So A will cancel out and E is equals to nu by 2 epsilon naught. So students, this is what we were searching for. So this is so simple in the when wire last case we did, there we take E dot S is equals to Q enclosed by epsilon naught, and there in that case curved surface area we have taken, and because the flux through other surfaces was 0, so and we simply wrote E into 2 pi RL the surface area. So here there is a plane surface area, so we have not written the area means the this pi r square or whatever, because it is going to cancel out, but there it was not cancelling out. So because this charge was equals to lambda L upon epsilon naught, so there L was cancelling out, and simply you get the answer that E is equals to lambda upon 2 pi r epsilon naught. So see, in both the cases this is, so students, by analogy you need to understand physics, that there in that case, in this case, what's the difference? So here simply cutting out, it means, see the beauty of this formula. So this is your plane sheet, so and these are the charges. So point can be anywhere, even here, here, here. It does not depends on the distance. So electric field only depends on the, it only depends on the surface charge density, only depend on this, because epsilon naught is constant, so only depends on surface charge density and does not depends on the distance. So but it is supposed to be near, because so that's the formula. So here it was depending on the R of the Gaussian surface, but it is not depending on anything. So E is sort of constant for little distances. Now we will write it in vector form. So in vector form we can write, so in vector form you can write this E equals to nu upon 2 epsilon naught n cap. So n cap is the direction, so this is n cap and this direction, so means coming out basically. So again n cap is the normal vector to the plane. What is n cap? N cap is normal to the plane. Obviously it is a unit vector, normal to the plane and going away from it. So this side also going away from it, this side also going away from it. So this was, I just written it for the case of uniformly charged wire. That was our case number 1, just to tell you the analogy. So obviously you are not going to write it in exams where if this derivation came. So this is just for comparison, I have written it. Okay. Now E is, now direction of E, we can write little bit that E is directed away. From the plate if the sigma is positive, and towards plate, towards the plate if sigma is negative. So this is the derivation of field due to uniformly charged infinite plane sheet. Students, the next topic, field due to uniformly charged thin spherical shell, is not, will not be there in the exams in this session 2021. syllabus has been reduced, but this is also simple. So let us write the formula if not deriving. So in case of spherical shell, the electric field at a distance, so this is a shell with radius r, and field outside the shell will be given as, so this is suppose the shell has positive charge, it will reside on the surface and it will behave like whole charge is concentrated at the center Q. So that is what is it equivalent to. So this is plus Q charge spread, but it behaves like the whole charge concentrated at the center. And suppose this is distance r, or this is, so you know the formula of electric field. So formula of electric field is kq by r square, and this radial, this is vector n cap in this direction, so this will be n cap, so that it's that you can write n cap, or the position vector, so you can write this. So it's the same formula, students. So the electric field at any point which is at a distance r is given by like the whole charge concentrated at the center, and field inside the shell is 0. So field inside the shell is 0, outside the shell same. So now let us do some important exercise questions. So please open page number 46 of your NCERT books. So let us do some important questions. Like the first question in your book is, what is the force between two? So let us do NCERT questions. So question number 1. What is the force between two small charged spheres having charges of 2 × 10⁻⁻⁷ Coulomb? So we have two charges, 2 × 10⁻⁻⁷ Coulomb and 3 × 10⁻⁷ Coulomb, and they are placed 30 centimeter apart. So 30 centimeter means 10⁻⁻², so that much is the distance apart, and they are in air. So now you have to find the force. So Coulomb force is given by F is equal to, just writing the magnitude, K Q1 Q2 in the modular sign divided by R square. So just simply put the values. So this will become 0.3 meters. So putting these values, and you will get 6 × 10⁻⁻³ Newton. So that's your R, this is your Q1, and this is your Q2. And K, value of K, you know, is equals to 9 × 10⁻⁹. Not writing the units, just simply put this value of K. So now what about the direction if you are asking the force? So the direction is, so the force is repulsive in nature, because like charges both are positive, so force is repulsive in nature. Next question. So again is this question, you have a small sphere of charge 0.4 microcoulomb, and there is another sphere of charge minus 0.8 micro. So opposite charges, so they are going to attract each other. So, and force is given to you here. and force is equals to 0.2 Newton. So what is the distance between the two spheres? So here R you have to calculate. So 9 into 10 raised to power 9 into microcoulomb. So micro means 10 raised to power minus 6. So 4 into 10 raised to power minus 6 into 0.8 into 10 raised to power minus 6. So not taking the signs because we are writing the magnitude only. We know that the force is attractive in nature. So divided by R square. So you can find the value of R comfortably, and R will comes out to be 0.12 meters. Now, what is the force on the second sphere due to the first sphere? So obviously, according to Newton's third law, F12 is equals to minus F21. So what is the force on the second to first? So forces are equal and opposite. That is what Newton's third law is. So obviously their magnitude is equal. So F12 is equals to F21 is equals to 0.2 Newton. So force on the second sphere due to first is, so this was the force, suppose 1 on 2, and this is the force 2 on 1, that is 0.2 Newton. Force on second due to first, and it is attractive. So these are very simple questions. Now 1.3 you can do yourself. 1.4, electric charge is quantized. What does this mean? So question number 4, charge is quantized means Q is equals to plus minus NE, where N is equals to 1, 2, 3 and so on. So you can write Q is equals to NE, where N is equals to plus minus 1, plus minus 2. So if charge is there, obviously it will not be 0, because if some charge is there. So that's how we write that charge is quantized. Now why do we ignore quantization of charge when deal with macroscopic large scale? So there you can assume that from a heap of wheat, if you take out 1 grain, it doesn't matter. So it's something like that. So because E, the elementary unit is 1.6 into 10 to the power minus 19 Coulomb, and if the charge is suppose 1 microcoulomb, so that is even 10 to the power minus 6 Coulomb, still taking out 1 or 2 electron doesn't going to affect 10 to the power minus 6 Coulomb. So that is why the greeny charge, the greeny thing is lost. So when we talk about, so we can ignore the quantization of the charge when we are dealing with the charge at this much of a scale. So because subtracting this minus 1.6 into 10 to the power minus 19 Coulomb, subtracting 1, if you are taking 1 electron out from there, it is not going to impact this much. Even 10 electrons, still the charge of 10 electrons will be minus 18. Still subtracting this out of this, no, because this is 10 to the power 13 times more than the charge of electron. So taking out 1 or 2 electron is not going to impact. Even 100,000 electrons you are taking out, still it will not be impacted. So that is why this quantization thing doesn't work when the charge is of this scale. Next question is, when a glass rod is rubbed with silk cloth, charges appear on both. So a similar phenomenon is observed with other pair of bodies. How can you explain how this observation is consistent with the law of conservation of charge? So when we have a glass rod So this glass rod, and you have rubbed it with silk cloth. Then plus q charge, so due to friction, charge transfers, and plus q charge on the rod and equal minus q charge on the silk. So plus q, because electrons transferred when you were rubbing, electrons transferred from glass rod to silk. That is why it has excess electrons, so that is why negative charge, it has lower electrons, so positive charge. So obviously the charge is equal and opposite because net number of electron transferred and received is same. So earlier also the net charge was 0, and finally also the net charge will again be plus q minus q will again be 0. So that is consistent with the law of conservation of charge. So that was question 5. Now question 6. Four-point charges QA, QB, QC and QD are located on the four corners of the square. So this is the square that we have, ABCD. So this is A, B, C and D, and 4 charges are placed over there. So this is 2 microcoulomb minus 5. So this is millicoulomb, this is microcoulomb, this so they are all in microcoulomb. So 2 microcoulomb minus 5 microcoulomb, and then minus 5 and 2 again. So A, B, C, D. So A, B, and then at C it's 2, and then again at D it is minus 5. So the charges are this. They are located at the side is 10 centimeter. So what is the force on a charge of 1 microcoulomb placed at the center of the square? So center of the square is where the diagonals bisect perpendicular to each other, and this is the point where I have placed charge 1 microcoulomb. So it is quite clear that attractive force between these two, and repulsive and attractive and repulsive. So what is the force on this charge? So force on this charge by superposition principle we will be using. But the important thing is here is that this plus 1 coulomb charge will be pulled on this side by this minus 5 microcoulomb charge. Again minus 5, so again it will be attracted on this side. So both the forces are same because force is equals to K Q1 Q2 by R square. So the distance, because the diagonals of the square bisect each other even at 90 degree, so both these distances are same, and charges are also same, product of the charges, and the forces are in opposite direction, so they will cancel out each other. So these two forces cancel out each other by symmetry. And here also this is 2 microcoulomb, so it will be repelled due to this, and due to this also it will be repelled in this direction. So again these forces will cancel out each other. So the charge distribution is symmetrical, and the forces are cancelling out each other. So net force will be equals to 0. So net force is 0 due to symmetry of charges. Next question. An electrostatic field is a continuous line. It means the field line cannot have a sudden break. Why? So it obviously exists at all the points, and these are the properties of the electric field lines, that they are continuous curves and they do not cross each other. But here the question asked is why they are continuous. So can you think the answer why they are continuous? So electric field lines, of course, they are throughout the region of the, so if this is charge Q, the field line obviously will be continuous. So if there is field at this distance r, so obviously if this distance r dash, so field will also be there, electric field radially outwards. So it starts, because it starts from, if it is positive charge, it starts from the charge and it goes diminish into at infinity. So it ends at infinity, diminishes at infinity and starts. And if it is negative charge, then it starts from infinity and it ends at the charge. So that is why there is no discontinuity. They are continuous. They cannot have sudden breaks. So it is gradually decreasing as you move away from it. Here also, obviously it is decreasing as you move away from it and increasing if you move towards it. So continuous curves. Now another question is very important, and this has been asked in the exam many times, that why they do not cross each other. So suppose if electric field lines cross each other, so these are the two field lines which are crossing each other. So I want to find the direction of electric field at this point. So one student will draw tangent at this point. So that's the direction of electric field, sir, due to this curve. Okay, but I want to draw tangent of this curve. So this is the electric field at point P due to this curve. So which is not possible. So which is absurd, not possible. So hence two direction. So if the two lines intersect, there will be two tangential. So if electric field lines intersect, there will be two directions of electric field at the point of intersection, which is not possible. So hence, so this is not possible, that two field lines. So hence they do not cross each other. Now we have question number 8 of the exercise. 2-point charges, which is QA and QB. So we have 2-point charges which are located 20 centimeter apart in vacuum. Find the electric field at the midpoint of the line AB joining the two charges. And if a negative charge of magnitude this is placed at the center, find the force experienced by the net charge. So we have 2-point charges QA and QB. So this is 3 microcoulomb, this is minus 3 microcoulomb, and they are 20 centimeter apart. 20 centimeter is 0.2 meters. What is the electric field at the midpoint? So this is I need to find this is the midpoint. Suppose this midpoint is O, this point A, and this point B. So the electric field at point O will be equal to electric field due to charge A plus electric field due to charge. Now the electric field due to charge A, what is electric field? Electric field is equals to K Q. So electric field due to Q is KQ upon R square. So that's the magnitude. So the distance, this is 0.1 meters, and this distance also 0.1 meters. So you want to find out electric field at this point. So what's the magnitude of the field? So magnitude of the field will be K Q. So the magnitude is same. So that is Q is 3 into 10 raised to power minus 6 Coulomb divided by R square 0.1 whole square. And let us write this direction as along. So if you put plus 1 Coulomb charge, it will be repelled by this, or the field lines will come out. So both cases you can find the direction very easily by putting plus 1 Coulomb charge. So if you put plus 1 Coulomb charge, this is plus 3, so it will be repelled. So direction is along OB. Plus for EB, this is the same magnitude, 10 to the power minus 6 Coulomb divided by 0.1 meters. So if you are writing Coulomb here, you can write meters, but even need not to write Coulomb. So what is it along? So if you put plus 1 Coulomb, so obviously this will be attracted towards this. So here, due to QA, due to plus 3, it will be repelled, so along OB, but here a minus sign, so it will be attracted. So field lines are towards the negative charge, and here the field lines are away from the negative charge. So in both the cases, it is along OB only. And this comes out to be, so just multiplying it by 2 and you can find it out. So this is 5.4 into 10 raised to power. So K you can put 9 to 10 raised to power 9, and this comes out to be 5.4 into 10 raised to power 6 Newton per Coulomb along OB. Simple addition. Okay, now second part is that what if you put here a charge that is Q naught, and Q naught equals to, you can take it as Q naught, it's a negative charge of minus, so you can write minus 1.5 into 10 raised to power 9 minus 9 Coulomb. So that's what this charge is. So what is the force experienced by this charge? So this will be the now. So force experienced by this charge will be given as F is equals to, force is equals to QE. So E is given to us. So there are two ways, either find the force due to this and then find the force due to this, but the beauty is that we know the value of E at this point. So E is representative of 3 Coulomb and minus 3 Coulomb, and E is independent of, this is independent of test charge. So this is your test charge that you have placed, minus 1.5 into 10 to the power 9. So we know F is equals to QE. So now this force is equals to QE. So F naught is equals to, so let us write the magnitude. In terms of magnitude, if we write, so in terms of magnitude, it is equals to Q into E. So E is this, Q is 1.5 into 10 to the power minus 9. So when I'm taking magnitude, this is the magnitude of this also, the magnitude of E also. And 1.5 into 10 to the power minus 9 equals to 5.4 into 10 to the power 6. And this comes out to be 8.1 into 10 to the power minus 3 newtons. So obviously, and so this is a negative charge, so it will be repelled, so force will be in this direction, and this is negative plus charge, so it will be attracted towards it. So in both the cases, the force is along O to A. This is negative, it will be repelled in this direction. This positive, this negative, it will be attracted. So that is why along OA. So that's the answer. So the force on the negative charge acts in the direction opposite to the direction of the electric field. That's all for today, students. So this was the 4th video. The first 3 videos are there on my YouTube channel. I hope you have liked it. Kindly subscribe this channel. See you tomorrow. We'll proceed further with the NCERT examples, and after that we will do CBSE questions. Just do these questions again, make notes all by yourself, and if there is any doubt, watch the videos again. See you tomorrow at 8 o'clock. Until then, goodbye.